Hi everyone, welcome to the forum on robotics and control engineering, or shortly FoRCE. I am Tansel Yucelen, and I am an assistant professor at the Department of Mechanical Engineering at the University of South Florida. And here I am also the director of Laboratory for Autonomy Control Information Systems, LACES. So with the support from my university, I am very proud today to host Dr. Necmiye Ozay from the University of Michigan to participate in our live seminar series on control systems through the FoRCE. And recently, you can also find all FoRCE videos at the IEEE Control Systems Society webpage. Link. So within a week or two, you can find also Dr. Necmiye Ozay's talk there, and you can access to all previous FoRCE speakers. All right, so shortly, FoRCE is dedicated to provide free, high-quality outreach events and online seminars to reach broader robotics and control engineering communities around the globe. And to support our mission, we periodically invite distinguished lecturers like Dr. Ozay to give talks on recent research results related to robotics and control engineering. So FoRCE aims to connect academicians and government industry researchers or practitioners with each other through cross-cutting research and education discussions. So before I formally start introducing Dr. Ozay, I would like to mention a few words about the WebEx. During the presentation, we are all muted. So if you are right now unmuted, please mute yourself to prevent a chaos. And you can ask questions after the presentation, and you can basically, the best way to do it based on the many FoRCE talks, you can send your question to the chat box, then I can read your questions to Dr. Ozay. And also, session is being recorded to be posted to the FoRCE website and also IEEE CSS video library website, and also to put to the YouTube. All right, so again, I am very proud today to have Dr. Necmiye Ozay, and she received the Bachelor of Science degree from Boğaziçi University in Istanbul in 2004, Master of Science degree from Penn State University, University Park in 2006, and the PhD degree from Northeastern University, Boston in 2010, all in electrical engineering. She was a postdoctoral scholar at Caltech between 2010 and 13, and she joined the University of Michigan, Ann Arbor in 2013, where she is currently an associate professor of electrical engineering and computer science. Dr. Ozay's research interests include hybrid dynamical systems, control, optimization, and formal methods with applications in cyber physical systems, system ID, verification, validation, autonomy, and dynamic data analysis. Her papers received several awards, including a nonlinear analysis hybrid systems prize paper award for years 2014 and 16. She has received the 1938 E Award and the Henry Russell Award from the University of Michigan for her contributions to teaching and research, and 5 Young Investigator Awards, including the NSF Career. So for all of you who are here live for the presentation of her, first I would like to thank you, Necmiye, for participating in our forum. And we are ready whenever you are. You can go ahead and start.
Okay, thank you, Tansel, for inviting me and for the nice introduction. So I am on sabbatical this year, so I am not that much used to delivering online content. Hopefully this is going to be fine. And there might be some background noise because my neighbors are having a construction, so hopefully it won't disturb us too much. So today I want to talk about some of the recent work that we did in my group. It's about control synthesis for large collections of systems with counting constraints. And I will explain what I mean these large collections and counting constraints during the talk. So this is mainly the work of my first PhD student who graduated now, Petter Nielsen, a second PhD student, Yunus Şahin, who defended last month. And this is mainly motivated from collaborations with my colleague Johanna Matthew who works on power systems. Okay, so what is the motivation? We are surrounded with like large-scale, complex distributed sensing, actuation, and control systems, from smart grid to manufacturing and automation systems, security and surveillance. These systems are around us. These systems are operating. But in the design, we are lacking certain guarantees. And there are two things that makes designing such systems and giving guarantees on their performance really difficult. The first observation is there is a very large number of both discrete and continuous states and decision variables if you look at these systems. The second observation is the requirements that we expect these systems to achieve, they are really complex. And as a result of this, we need complex controllers that are hard to design by hand by individuals. So there's some automation need here to make these designs process more smooth and also hopefully to give some guarantees to the design process. So scalable tools, when you look at these systems, both for data analysis, control design and verification, both in terms of theory and algorithms and software, they are lagging. And we are trying to sort of fill this gap and develop scalable tools for control design, data analysis for these type of systems, and verification. And in this talk, I will mostly talk about the control design part. Okay, so the broad area that my research fits in is formal methods in control. And these are model-based approaches where we use models for the system itself. These models are usually ODEs, but mostly hybrid or switched ODEs. They might have continuous and discrete inputs. They might have disturbances and parametric uncertainty. We also use models for the environment. These could be models on your disturbance or other external environmental events that doesn't directly affect your dynamics, but you want to react to those events. So these could be faults or other external events. We formalize assumptions and requirements in a way that they are amenable to mathematical analysis. And for this, we use temporal logics, linear temporal logic and its extensions like time temporal logics. And there are methods that we work on for verification and synthesis. And verification question is close to the analysis question that we are used to in control. In the verification question, you have a system, you have a specification, and you already have a controller in place. And you want to make sure, or you try to answer this question, whether with this controller, my system satisfies the specification under my assumptions. If this is true, you want to give a certificate or proof of this fact. Or if this is not true, you want to produce a counterexample showing that there is a scenario that satisfies all your assumptions. However, your system is still failing the specification. This is verification question. The other question that we are interested in is the synthesis question. Synthesis question can be thought as a quantified version of the verification question, where I have my system model, I have a formal specification. However, I don't have the controller in place. And the question we ask is, does there exist a controller such that if I close the loop around my system with this controller, the specification will be satisfied? If this is the case, you expect your synthesis algorithm to produce such controller together with the guarantees that this controller satisfies the specification. Or you want to produce a proof that no matter what you do, this system is not capable of satisfying this specification, so there exists no controller. And you want to provide a proof that such controller does not exist. And in this case, the designer needs to go back to their plant and maybe change things in the plant, put more sensors, put more actuation, or they need to relax the specification. So they are asking too much given the limitations of their plant. These are two main questions. And these are studied a lot in computer science when you have discrete models of your system. And we are trying to bring these tools to more control models with differential equations and try to answer these questions in certain instances. Why I am saying in certain instances, when you start working with continuous spaces, vector fields, these questions become, in general, undecidable. So we are trying to identify subclasses of systems and subclasses of specifications where we can give algorithms that can do verification and synthesis. So I will mostly talk about synthesis in this work. Again, synthesis, as I said, there's a system model, there's a formal specification, and we are trying to build this synthesis engine. And let's take a closer look at the type of models that we work on. So we typically work with differential equations. These are continuous time models, or difference equations, which are discrete time models, where there's a state, there is some continuous control input, there is some discrete control input. These could be switches or valves in your system, so you can make discrete decisions. There is a continuous disturbance input, and there are discrete uncontrollable inputs. So you can think about these discrete uncontrollable inputs like things like if you are designing a controller for an autonomous vehicle, this discrete uncontrollable input could be the traffic lights. You see red, green, yellow, and you want to react to that. And the characteristics of the control problems that we are interested in is there are hard constraints, both on the inputs, so we don't have unlimited control authority, and on the states, so you want your states to remain in certain safe parts of your state space. We have specifications that are infinite horizon. It's not that we are only interested in stability and properties that hold asymptotically in the limits. We care about both the transient part and the steady state part. Therefore, we are interested in guaranteeing correctness all through this infinite horizon. The systems are hybrids. Even the system is not hybrid, the control needs to be hybrid in most of the cases because your specifications are complex. So there's both discrete and continuous parts of this problem. And in the end, you want to be robust to disturbances and reactive to this more discrete inputs from the environment. The part that I want to focus on in this talk is the size of the state space, the continuous part of the state space, which I show as Rn. And I am interested in trying to understand what happens when n is large. How do I scale methods when n is large? So let's look at the landscape of current methods and what makes it hard to scale these type of approaches. So as I said, I will look at state space dimension. So that's one of the factors that makes it hard to design algorithms. So as the state space dimension gets larger, the algorithms suffer from curse of dimensionality. The other factor that affects scalability is the complexity of dynamics. For example, if you have a linear system, maybe your algorithms scale a little better. If you have nonlinearities or hybrid systems, complexity becomes an issue. The complexity of the specification also affects the scalability. So maybe reachability and invariance, those are simpler and you can come up with more scalable algorithms in this case. But if your specification becomes more and more complex, the scalability with respect to the specification size becomes an issue. There is the strength of the conclusion, whether you want to come up with a complete algorithm that gives yes and no answer definitely, or do you just want an algorithm that when it finds an answer, it's correct, but there would be cases the algorithm will say, oh, I don't know. Accuracy of results is another thing that affects scalability. Do you want really correct algorithms, or are you okay with approximations, given that there is some bound on the approximation? And ability of handling certain types of non-determinism and uncertainty, and whether you can achieve tasks with open loop controls versus you really need feedback is another thing. And in this talk, I will mostly focus on state space dimension and scalability in that context, but other top two aspects will come into play as well. So let's look at the state-of-the-art informal methods and what these methods can deliver so far. So we can handle hard state and input constraints. We can handle hybrid dynamics, and we can handle fairly complex specifications. And there is work out there in the last 10, 15 years doing all of these, but they are constrained to really small state space dimensions. If you look at the applications, they have very simple robotic bicycle model or unicycle model type models. There are some building thermal management type applications, again, very low dimensional state space. There are applications in vehicle control, traffic control, but usually state space dimension is at the order of 4 or 5 at most. And here are some references of different types of results and their scalability. Here I put system dimensionality on my one axis and specification complexity on the other axis. Of course, as any literature review, this is probably incomplete. But if we look at this picture, we see that invariance type properties with linear systems, these are things that are studied in control for a long time. If you look at viability literature or reference governors, there are really scalable methods out there. We can do things up to 15, 20 dimensions there. Then there are other methods based on sum of squares or Hamilton-Jacobi-Bellman type equations when you combine invariance and reachability. Here I am using box to mean invariance, diamond to mean reachability. So the first type of specifications are invariance specifications. The second type of specifications are invariance plus reachability. Then we have this linear temporal logic type specifications that people looked into certain fragments of linear temporal logic. Don't allow everything that you can specify with linear temporal logic, but look at the subclass. And there are integer linear programming type methods to handle those things that are maybe not too scalable. And when it comes to using full LTL, the scalability goes down even further. So there are also methods for medium scale systems. For example, people use monotonicity type ideas in the dynamics. So now you start looking into your dynamics a little carefully and try to extract something that you can use. There are multi-scale abstraction type incremental methods where you zoom into different parts of your state space depending on how relevant they are for your specification. And there are compositional approaches where if you have a network system and if there is a clear subsystem structure, you try to do something by subsystem and subsystem by subsystem and try to compose them in the end by keeping some of the correctness guarantees. So in my group, we did some work on these medium scale systems, and here are 2 examples of the work that we did. So one on compositional synthesis for autonomous driving functions. So we looked into the system and we realized in the domain of vehicle dynamics, people study longitudinal control and lateral control as two separate control problems. However, there is some interaction between longitudinal control and lateral control. For example, you cannot move laterally if your longitudinal speed is 0. But if you look at closely to the dynamics has the form that I have over here. So let me try to show. I don't know if you can see my.
Okay, it runs pretty smooth.
Okay. There is this x1 dynamics and x2 dynamics. X1 dynamics is linear in x1, where some of the system matrices depends on x2, and dynamics is linear in x2, and some of the system matrices depend on x1. So we realize there's this type of structure in these longitudinal ladder dynamics, and we can quantify the interdependence between different subsystems and design controllers separately for these subsystems and put them together. And in the end, you are solving a 7-dimensional nonlinear problem with guarantees. However, the individual problems you need to solve are much small dimensional. So there's another example that we looked into with researchers at Ford, where we looked into thermal management for fuel cells. There's both discrete and continuous actuators in the system. The specification is very complex, so there are batteries and other power split modules. There's thermal properties you need to take care of. There are power properties, and the system is highly nonlinear. And in this case, we realized the system looks mixed monotone, but we couldn't find results in the literature that would certify mixed monotonicity of the system, and we generalized the existing mixed monotonicity results to be able to certify mixed monotonicity of the system, and then used monotonicity type ideas to design controllers. We also put some of these controllers on a real car, not the fuel cell one, but autonomous driving one, when M-City was open. For those of you who don't know, at University of Michigan, we have this live test bed or test center. It's an outdoor lab. It has a highway portion and city portion, and we have a couple of vehicles there where we can test algorithms, and we synthesize a controller. And here in this video, the controller that runs the vehicle, it's not hand designed. It's an algorithm. We just give the system model and the specification. Algorithm synthesized the controller, generated the code, and we just put the code on the controller. And one thing, for example, we realized when doing this is we weren't taking into account delays in actuation, but apparently in vehicles, there is this non-negligible delay from your actuation, especially in steering, to the actual motion of the vehicle. And some of the things we realize, if you are trying to do control, ignoring that delay is okay, but if you are trying to do supervision of a human driver, and if the human driver is incapacitated and they start operating at the limits of your safety, those delays become important. Then we started thinking about, okay, what happens with delays? Systems with delays are high dimensional. Can we scale our approaches? And we have, for example, a paper that we are going to present at ACC this year that shows that although delayed systems are high dimensional, if you want to compute invariance for these systems, you can do your computation in a very low dimensional space. So this is what happens with medium scale. There's also large scale systems, and there were results out there for large scale systems where now the system dimension is hundreds or thousands. But the existing results were not for synthesis. So there were results for verification by Taylor, Johnson, and Cheyenne Mitra. There were results for abstractions for these large collections of systems by Sujani and Abate, but there weren't that many results for synthesis. So one of the things that I want to mention, and also in the examples that I showed from my group, when you start talking about medium scale or large scale, there's a recurring theme here. You don't go and look at x that equals f of x. You start looking at the structural properties of your dynamics. And you are trying to exploit these structural properties to come up with smarter algorithms. And we'll try to do this same thing. We will try to identify a structural property and use it in our algorithms to design controllers. So let me go back to the topic of the talk. I told you I will talk about large collections of systems. Let me give you some examples of large collections of systems. So the first example is an emergency response scenario with a robotic swarm. We want to deploy a large number of robots. Maybe you have quadrotors, you have ground vehicles, and we have a search and rescue mission. We want to plan trajectories that are dynamically feasible for each of these robots. And our requirements are in the form that we want to send sufficiently many robots in certain areas. For example, if you have a victim somewhere identified in an earthquake, maybe you want to send your 3-4 robots at the same time so that they can help the victim. Maybe there are certain regions you don't want to stress too much by sending too many robots. So there are specifications like not too many robots in certain region. Again, imagine an earthquake. There's a bridge that got damaged. You don't want to send too many ground robots on the bridge because that risk the collapse of the bridge. And there are collision avoidance and charging reporting type constraints for the individual robots in your collection. So one example. Let me show you another example from a domain. This is coming from smart grid power and energy domain. This is coordination of thermostatically controlled loads. For those of you who don't know what thermostatically controlled loads are, these are roughly anything in your house that has a thermostat in it and that does on-off control. So the examples are refrigerators. There's a temperature control unit in your refrigerator, and it gets too hot, it starts cooling, and if it gets too cold, it starts heating. Actually, it doesn't heat in the refrigerator, it just turns it off. Similarly, air conditioning units work with the same idea, and water heaters in the houses, they work in with the same idea. And there are thermal dynamics in these systems that are controlled with on-off switches. And the requirements from the perspective of the grid operator is that the grid operator doesn't want too many of these thermostatically controlled loads to be on at the same time, because when these devices are on, they are all extracting power from the grid. And imagine a neighborhood with thousands of these devices. You don't want your devices to synchronize and start extracting power all at the same time, because that really puts pressure on the grid. And some blackouts during summer in New York, maybe 10 years ago now, was due to these type of problems where grid get overloaded because of the air conditioners. But at the same time, the grid operator might want sufficiently many of these devices to be on, because if you have some renewable energy in the grid, these devices can store that renewable energy in the form of thermal energy. So you want to utilize, when there's additional power in your coming into your grid, you want to utilize these devices as a storage unit when you think about the devices as a collection. But although the grid operator wants to do these devices sit in our households, and as customers, we don't want to be inconvenienced, and we really want the local temperature constraints that we set to be satisfied. And there's work in power and energy literature trying to understand whether if these devices give some part of their control to a central authority and participate in the so-called demand response type programs, what can be achieved in terms of grid stability and utilization of these renewable energies. So I showed you two examples that look quite different, but as I said, there is a common structural property or a couple of common structural properties in both examples. So the first thing you might want to observe here is that there's a large number of systems. So if you are trying to control water heaters and fridges in a neighborhood, if there are thousands of households, there are thousands of water heaters and fridges and air conditioners. Similarly, in a robotic swarm, there's a large number of robots in your swarm. However, there's a small number of classes. So if you have a robotic swarm, not each robot in your swarm is different. So maybe you have UAVs, but almost all your UAVs has the same dynamics. They are coming from the same manufacturer. Maybe you have ground robots. Maybe you have two different types of ground robots, but the similar brand ground robots have similar dynamics. So there's a large number of systems, small number of system classes, and systems within a class are almost identical. That you have, we call them counting constraints. You really care about how many of these systems are in a given mode, or how many of these systems are in what region of the state space. So you really care about these numbers of systems in a sense. And the third thing is that identity of the individuals is not important within a class in terms of satisfying the specification. So if I only care about the total power extraction from the grid, at a given time, I don't care if my air conditioner is on versus my neighbor's air conditioner is on. From the grid's perspective, grid differentiate us. Similarly, if you want to send 5 quadrotors to help monitor a region, you don't really care which quadrotor goes there. As long as 5 goes there, the mission will be accomplished. So for simplicity, initially what I will assume is dynamics are identical within each class. And without loss of generality, I will assume there is only one class. And I will show you extensions for both of these simplifications. So let me now try to mathematically write down this problem. And I will try to mathematically formulate the problem for this thermostatically controlled loads first. Let's say theta is the temperature of one of these devices. And the dynamics of the temperature, theta dot, evolves with respect to 2 different vector fields, depending on whether my device is on or off. So theta dot is equal to F on if my device is on, and theta dot is equal to F off if my device is off. And here I is the identity of the device, and I have a large collection of these devices in a neighborhood. Say I goes up to n, and n is a large number. So from the customer's perspective, the control problem involves each customer's room temperature or house temperature to be close to a desired temperature range. Let's call this theta I desired. And we allow small deviations that the customer won't notice. But we want to ensure that the true temperature remains within a delta distance from this desired temperature. And the utility company, the grid operator, wants to control the aggregate demand, meaning they want to control the number of devices that are on or off at a given time. And here we are assuming these households are signed up for this demand response program, so the grid operator can turn on and off these devices as long as they satisfy the constraints in one. The grid operator, as I said, the utility company wants to control at each time how many devices are on. And here I am showing it with an indicator function 1. And I am just counting the number of devices. Among n devices, how many of my devices are on. And the goal is to find the switching strategy for each individual device such that it exploits the flexibility in one. So it wants to use that temperature range so that it can control the number in the second equation here. I can write a more general form of this problem. Say I have n identical switch systems with m modes, where for each individual system, I am trying to design this switching signal sigma, take different values. There are mode-specific unsafe sets. For each mode, I want to avoid certain regions. Going back to the TCL example, if I am heating the device, if I am in the heating mode, there's an upper temperature and I want to be sure I am always below this upper temperature. And if I am cooling my device, there's a lower temperature and I want to make sure I am always above the lower temperature. And if I am not above, maybe there is some trigger and there's a forced mode switch. And there are these mode counting bounds where I want to make sure the number of devices at a given time in a given mode is lower and upper bounded by 2 numbers at all times. We want to design or synthesize the switching strategy sigma I, possibly different switching strategies for each device, in a way that 3 is satisfied all the time, while we are observing this local safety constraints per device by avoiding the unsafe sets. What is the structural property here? So one thing we observed that if we assume these devices are identical, and if you assume you stack all the states of all devices together, this large-scale system is permutation invariant, both in terms of dynamics and in terms of specifications. So what I mean by permutation invariance is the following. I have 2 identical devices. I have a switching strategy for device 1 when it starts from a given initial state. And I have another switching strategy for device 2 if it starts from a given initial state. If I swap the initial conditions of these devices, I can as well swap their switching strategies, and I will still satisfy the specification. So I can swap my switching strategies and initial conditions, and this won't change the satisfaction of the properties. And this is the property that we want to utilize to be able to coordinate a large collections of systems of this form. So I can stop here a little bit to see if there are any questions. Okay, So if the problem setup is clear now, I will show you how we go about solving this problem. So the first thing we will do is we will take an individual device and we will forget about the rest. And we will construct a discrete abstraction, a symbolic model for this device. Since individual devices are not necessarily high dimensional, we can do this. Then we will try to aggregate different discrete abstractions into a single abstraction. Then we will analyze the structure to understand some fundamental properties. Then we will propose an optimization-based solution, and I will show you some analysis of the solution. So as I said, first step is constructing a symbolic abstraction, a finite transition system that represents the dynamics. And to do so, we will use this idea of epsilon approximate by simulations. Essentially, what we will do is we will take a device, we will take one of these subsystems, we will take its dynamics, and we will fix the mode, and we will look at the flow, how the vector field flows. So for each grid point, we will grid up the state space of this device. We will just simulate the vector field starting from that grid point for some time sampling tau. And we will look at which point that simulation ends at, or closest to which of these grid points that simulation ends at. We will just round that simulation to the closest grid point, and we will just put a transition in the graph structure. And we will do it both for heating mode and cooling mode for if you have another device or another problem with different modes of operation, you will do this abstraction process for all of your modes and all of the vector fields there. So one thing to note, if your devices are identical, I just need to do it for one device or one of the systems, and all the systems will have this same graph that represents that. So what do we know about these symbolic abstractions? If we assume the dynamics are incrementally globally asymptotically stable with some KL function beta n, meaning if the flow starting from two initial conditions when simulated forward will remain bounded, the distance between these two trajectories will remain bounded as a function of how close these trajectories are initially, and this bounds goes to 0 as time goes to 0. If our dynamics satisfy this type of property, then there is always a time discretization and a space discretization that gives us an epsilon approximate bisimilar model if we pick our time discretization and space discretization according to this formula. So what epsilon approximate bisimulation mean? I think I had it in the previous slide. That means that for each trajectory on my continuous dynamics, there is a piecewise constant input that generate, or for each path on my graph, there is a piecewise constant input that generates a trajectory on the actual dynamics. And if I time sample this trajectory, I will remain epsilon close to the grid points represented by this graph, and vice versa. So for each path on the graph, there's a corresponding trajectory, and for each trajectory on the system, there's a corresponding path on the graph if I pick my space and time discretization according to this formula. Okay, now I can do this discretization for different modes, and I will create this overall graph that I call a mode transition graph. So what are some properties of this graph? If I have a homogeneous collection of systems, as I said, each system will have an identical mode transition graph. And this mode transition graph will be deterministic in the sense that from a given node, if I pick a control input, there will be a unique node that I will go to. And this also works if we consider mild heterogeneity. So instead of identical models, if I have models of this form, where this D might be different parameters for different devices in your system, or different disturbances affecting different devices, if this bounded parametric uncertainty or disturbance satisfies a Lipschitz condition, then we can modify this time and space discretization slightly using this Lipschitz constant, so that we can still get this epsilon approximate by simulation. So what this says is that if I have similar systems, I can use this epsilon in epsilon approximate by simulation to construct a common representation for all systems that has similar dynamics. Now I have common representation. Instead of treating this as something that represents an individual device, I will treat this as a histogram. So what I mean by that, say I have 3 devices whose continuous state is close to a node here. I will just put a 3 at that node. If I have 2 devices on the upper right corner of their state space, I will put a 2 over here. In the end, this graph becomes something similar to a histogram, where each node represents the number of devices at a given time whose state is close to that node. Now, if we try to write down the dynamics on this graph by defining appropriate states and inputs, the dynamics looks like this. Let me try to explain it a little bit. So I will represent with WIM the number of systems in a given mode, node VK of this graph. I will represent with RK my inputs, in the sense that the number of systems at a given mode, at a given node, that I am switching from a given mode to a different mode. So say I have 3 systems over here, and in the next step, I want to keep 2 of them in blue and 1 of them in red. What would happen is that these 2 systems, 2 of them, for these 3 systems, 2 of them will remain where they are, and 1 of them will move over here. And if I try to write this, the dynamics looks like this. It essentially says the number of systems at a given node here in the next step is equal to the number of systems there currently, and the number of systems that I am switching to that node in the next step, and minus the number of systems I am switching out from that node. And if you look at this dynamics, it essentially can be represented with a linear equation. And here my control actions are how many systems I am switching from one mode to another at a given mode. And these control actions is also bounded in the sense that if I have 3 systems at a given node, I cannot switch more than 3 things in the next step from that node. So all the numbers over here should always remain positive. So this is a compact representation of my dynamics. What are some properties of these dynamics? The total number of systems should be preserved. So if you add up the numbers on my W state, that sum is an invariant of this system. This system operates in the positive orthant because all the numbers should be positive. And this system also operates on an integer grid because these are really counting the number of systems in certain parts of the state space, so these cannot be fractional numbers. So one of the things we can prove is that now that we have this linear aggregate dynamics, we can write down our safety properties and mode counting constraints as just linear constraints on these dynamics. So if I want to avoid certain parts of the state space, I just want to make sure the components of my state W corresponding to parts that I don't want to visit should always be 0. And if I want to count the number of states in a certain mode, I just sum up the coordinates of W in that mode, and these should be bounded between the two counting bounds that I have. So now I have a different problem, which is for a linear system with linear constraints. And one thing we can show is that this linear system with constraints problem, this constraint linear problem, is equivalent to my original switched system problem in the following sense. If there exists a control input for my linear problem that enforces the constraints 6 and 5, then that enforces the constraints 6 and 5 with an epsilon expansion of the unsafe sets, then there exists a solution to the original problem. And this epsilon expansion comes from the fact that I am using an epsilon bisimulation. And similarly, if there does not exist a solution to this linear problem for an epsilon shrinkage of my constraints, then there does not exist a solution to the original problem. So we reduce this ugly looking nonlinear switch system problem linear control problem with linear constraints. So we will focus on solving this problem. If this was a finite horizon problem, we know how to solve it. We can just write a linear program to solve it. It's kind of an MPC like this thing. But as I said, we are interested in infinite horizon strategy. So we need to take care of both transients and steady state. And to this, what we will do is we will focus on strategies that has two parts. So the initial part would be steering this system, this linear system, into some nice part of the state space and finding a periodic solution in that nice part. And if I can find a periodic solution, one thing I know is that by periodicity of the solution, if I satisfy the constraint in one period, I will indefinitely satisfy the constraint. So, as I said, the first part of the solution is steer the system into a nice state. And this is kind of a controllability-like condition. So can I always steer a system from a given initial configuration to a final configuration? And here, what I mean by state is a configuration of the histogram that I showed you. So one thing we can show is that if we put the mode counting constraints aside, the controllability of this linear system evolving on an integer lattice can be analyzed by looking at the properties of the graph that we constructed. And essentially, one of our results says this graph is controllable if the connected components of this graph has period 1. And the period of a graph, for those of you who don't know, is the greatest common divisor of the length of the cycles of the graph. essentially telling us when it is easy to control these type of collections or not. So, as I said, this is about the prefix part. Can I push my system or steal my systems from an initial state to a nice final state? And for the final state, what we will do is we will look at cycles of this graph. Because if I put a system on a cycle and start cycling over there indefinitely, then I will be creating periodic trajectories. So I have some slides about cycles. I will try to present them really fast. But the idea is that I will try to assign my systems into cycles. And I will use this alpha to represent cycle assignments. And I will try to count the number of on and off modes that I have to use to keep a certain number of systems in a cycle. So let me try to illustrate it with a simple example. For example, I have one short cycle here, one long cycle here. The assignment in the short cycle is 3, 0, 2. And the assignment on the long cycle is 1, 2, 0, 2, 3. So if I start operating my system, when for all devices in the 1 node, I will pick the blue. For all devices in the 2 node, I will pick the blue. And for all devices in this 2 node, I will pick the red input. And if I do that, these numbers will keep circulating around this cycle. And when they circulate around that cycle, I can count, in the worst case, how many red modes I am using. And in the best case, how many red modes I am using. And if red corresponds to the number of devices that are on, this will give me a bound on the maximum and minimum number of on modes that I am using when circulating over this cycle. So the nice thing about these cycle assignments is that although they look complicated, the constraints on these cycle assignments can be represented as linear constraints, where you just create a circulant matrix that shows how things evolve around this cycle assignment. In the end, I can combine everything because I write everything in terms of linear constraints. So we have this weird linear program. But essentially, there are mode counting constraints during the prefix. These are just linear constraints on my new state. Mode counting constraints during suffix. These are my cycle assignment constraints. Those are linear as well. There's a boundary condition so that my prefix ends on the suffix, on the cycle, so then I can keep cycling. Then I have system dynamics and local safety constraints. So the message here is that in the end, this is a linear program. I can impose integrality constraints and solve an integer linear program, or I can relax these integrality constraints and solve a regular LP. But the nice thing is that the number of constraints and variables in this program is independent of n. So we can scale arbitrarily well. So we have some completeness results about this. So if you have, if there's a solution, there's always a solution for this ILP for appropriately chosen prefix and suffix size. There are results regarding relaxations of this LP, relaxations of this integer linear program to a linear program. For example, using a linear program, you can give certificates of non-existence of solutions. And there are also results showing how you round the result of the LP and get a solution for the integer problem. And one nice thing here that we see is that relaxation to LP becomes more and more exact as the number of devices increases. So intuitively, what's happening here, I am running out of time. I will try to wrap up really quick. So initially, if you let these devices by themselves, they will go on and off. But with these choice of cycles, we are finding different schedules for different devices in a way that these schedules prevent these devices from synchronizing, and they are guaranteeing that the number of on and off devices can be controlled. So I have some density plots here as well. And I will try to end with a slightly interesting thing. So I talked about initially robots and thermostatically controlled loads. This idea of counting can be extended to robotic problems as well. And you can go from, oh, I want to satisfy these counts at a given time, to satisfying temporally evolving constraints on counts. And this can be represented with a logic that we call counting temporal logic. And with that, we can coordinate multiple robots in interesting environments. We can also handle things like asynchrony if your switching or control of these devices are not synchronous. You can still design controllers that will satisfy the properties that you want to satisfy in the face of asynchrony. So you can probably take a look at this video. We just put it to Georgia Tech's Robotarium. We synthesized controllers, and we just run some examples there. So finally, let me conclude here. So if we want scalability, what I want to argue is that we want to look into structure. If we just do x dot equals f of x, there is always a hard f, and that will prevent us from finding scalable solutions. But if you look at the structure in your problem, here we are exploiting symmetries and permutation invariants to come up with very scalable solutions. One nice thing about our solution is that it works both for 10 systems and 10,000 systems. So it's not a density limit only. So it works across different scales. It has applications in different domains. And we have some interesting extensions. And we are working on different variants of this new representation of collections currently. And going back to the original graph, so what we did is maybe we looked into a very specific type of specification, but now we can scale things in this logarithmic y-axis to thousands of systems or state space dimension that's equal to thousands for a specific class of constraints. So with that, I will probably end my talk.
Thanks, Necmiye. So thanks for your time and presentation. So if you like, I can start reading some of the questions from the audience.
Okay.
Okay, so the first question is from Anne Wood. I don't know the actual name. Why is limiting the discussion to only one system class considered without loss of generality? Are we assuming that the dynamics of multiple classes within a given system will always be mutually independent and thus can be treated separately?
So that's a very good observation. We are assuming individual systems, the dynamics are decoupled. If you have multiple classes, one thing that you can do is you create this graph for multiple classes. You append your linear program with new states corresponding to this new collection corresponding to a different class. But one thing you can do is your constraints might couple different classes. So if I maybe go back to my linear program. So what will happen is that there will be a W1 for class 1. there will be a W2 for class 2. You will have identical constraints for both classes. Then this, let me see, which one? These 3 counting constraints, instead of summing over a single W, you will add up the 2 different W's corresponding to 2 different classes whenever you see this counting related constraints. So it's just more constraints in your linear program. It's still going to be independent of the number of systems n, but the number of constraints you have increases linearly with the number of classes.
Thanks a lot. So another question is from Berk. Is there any loss of information with abstractions? Slide 17. That is, given a trajectory of the continuous time dynamics with piecewise constant input, is there a sequence of discrete states, epsilon close?
So there is no loss of information if you are doing it for a single system. Whenever there is a trajectory for the continuous system, there's a corresponding path in the graph. Whenever there's a path in the graph, there's a corresponding trajectory.
Thank you. One more question from Hamid Osare. So how do you take into account the background, unmeasured, uncontrollable usage of hot water in the water heaters?
So that's a very good point. So that's something we are trying to work on right now. So this is, when it comes to application, this is idealized a little bit. So one approach is, if I can represent everything with this bounded disturbance at different devices, I am okay. But we haven't studied how large those deviations become for different households and how big the bound on D gets in those cases. But making this a little bit more realistic is what we are looking at. So far, if those deviations are small, and if I can capture them as a disturbance in this mild heterogeneous version of the problem, we are fine. But if they are really large, then it would probably be a jump in this linear model. Yeah, that's an interesting future direction.
Thank you. And another question from Yu Wang. Thanks for your nice talk. Would you mind explaining briefly how to model check counting LTL? Specifically, how do you construct spatial automata for this logic in your robotic problem? Thank you.
So one thing we haven't done, so let me go to counting LTL slides. We haven't taken an automata-based approach here. So for synthesis, what we did is there are results in bounded model checking where you represent your LTL specification with SMT constraints, satisfiability modular theory constraint, if you are doing bounded model checking. And one thing we can do for counting LTL is something like bounded model checking. We came up with encodings, bounded model checking like encodings for counting LTL. And we used bounded model checking type ideas to model check and synthesize using this logic. It's interesting if there's an automata representation of this. So there are automata with counts, but at this point, we don't know the relation of counting temporal logic, counting linear temporal logic, and several more quantitative automata representations. So we haven't done that. For this, we just did bounded model checking, and we developed encodings for counting LTL for bounded model checking.
Thanks, Necmiye. One maybe last question from Luis. How can you guarantee observability for thousands of systems in this framework?
That's again a very good question. We assume state is available. That's a very big assumption, I know. But we assume we can access the state. So it's interesting what you can do if you have methods, if you have a sort of measurement equation and you need to do you need to build a state estimate. That's an interesting question. So that's also one of the things we are looking into as future work. So we are looking into, so far we are designing more or less open loop stabilizing trajectories. But we have a student right now with Johanna who is looking into closed loop invariant inducing controllers. And if we can do that, we believe we will be able to connect it to bounded error estimation type ideas to do output feedback. But so far, we are really assuming we have access to state to simplify things.
Thanks a lot. We received one more question. Maybe let's make this, if you have time, last question. From Shatwan to everyone. Thank you for your nice talk. Can you please clarify if one of the robots is out of control? Will it affect other robots?
So that's a good question. If you are doing a UAV type application, and if one of the UAVs falls out of sky, it won't affect anything. And you can also design your controller in a way that it will be robust to loss of individual robots. But if it's a ground application and if a robot gets stuck, then it might lead to deadlock. So that we don't know. For example, in this example, I have something like a bridge over here. And if a robot fails and gets stuck there, then we have no guarantees after that point. So one option is to try to resynthesize a new plan. But that's also a good robustness issue to that would be useful to look at.
All right, and Necmiye, again, thanks for the great talk, and thanks for your time, and thanks to all 90 people, participants. And with this, I would like to end. And can we say, if our audience have more questions, probably they will. Can they email you?
Sure. So my email address is just my first name, umich.edu. I don't know if. Yeah, you can go to my website and you can find my email address there. Feel free to email with questions.
All right, perfect. Thanks a lot. Thanks, everyone.
Bye-bye.
Bye.